Good day, everyone. All right, so in this video, I want to talk about 7.3 satellite motion in circular orbit, right? And in this part of the chapter, we talk about three things. Number one, the escape velocity. Number two, the velocity of a satellite orbiting a planet or a bigger mass bodied, and then the last one would be the period in which that satellite orbits. Okay, so let's look at the first one, which is the escape velocity. It is defined to be the minimum velocity such that the body is able to escape the gravitational pull. So say we have a rocket here, right? What is the amount of velocity? What is the velocity that is needed? Okay, this can be done by calculating by reminding ourselves that anything that moves, anything that has velocity must have kinetic energy. So it is max kinetic energy, right, at the beginning, and at the end it has to be equal to the gravitational potential energy. So what we mean by that is the gravitational potential energy, right, must be equal to the gravitational potential energy, right? Okay, so we know the equation for kinetic energy, which is half mv squared. So half m, the mass of the rocket times the velocity of the rocket squared, must be equals to the gravitational potential energy, which is simply g, the mass of the earth times the mass of the rocket over r. Okay, so if we rearrange this, we can cancel out the mass of the rocket. If we rearrange this, what we get is Vr square equals to 2g me over r. Okay, we can square root both sides, and what we get is the velocity of the rocket needs to be, right, 2g me over r square rooted to be able to escape the gravitational pull. So let me just rewrite that again. It's going to be Vr equals to the square root of 2g me, the mass of the earth, over r. Now say you are on Mars instead, or Venus, then the mass of the earth is simply the mass of that particular planet. Alright, okay, so next let's look at the velocity of a satellite. So by a satellite we mean here that is that satellite will be moving, or moving in a circular orbit around the earth. So we have the earth over here, and then let's say this is the path of that satellite. So here's the satellite, and that's the path of it. We are looking for its velocity, right? Okay, so for this particular derivation, what we need to remind ourselves is from chapter 6, centripetal acceleration, where centripetal acceleration is equals to v square over r. Okay, and then we remind ourselves gravitational acceleration, which is gm, mass of the earth, over r square, because these two are equal to each other, right? Because the gravitational acceleration is what allows the satellite to orbit the earth. Okay, so if we equate them both, what we get is v square over r is equals to g me over r square. Cancel out the r, take square root from both sides, and what we get is v equals to the square root of g, mass of the earth, and r. Okay, and that's the velocity of that satellite as it orbits the earth or whatever planet it may be orbiting. Okay, and the last part is to derive an equation for the period of that satellite. Now we define the period to be the time it takes for the satellite to orbit, let's say the earth, right, for one revolution, only one. Okay, so again, let's look at velocity. What do we mean by velocity? Velocity simply means the displacement per unit time. In its scalar form, we can talk about the speed, which is the distance over the amount of time given, right? So here, let's consider a circular path where the circumference is merely 2 pi r, right? And the time it takes for one revolution is the period, which is t. We can remind ourselves that this velocity is the velocity of the satellite from the previous slide, where it is equal to the square root of gm, m as in mass of the earth, over r, right? And this is going to be equal to 2 pi r over t. If we square root both sides, so let's say we square, sorry, not square root, we square both sides, right? What we get is gm e over r, which is equals to 2 pi r square over t, okay? T square, sorry. 2 square pi square r square over t square. We can bring this r to the right hand side and then bring this t square to the left hand side, okay? And we rearrange that so that it takes this form. T square equals to 4 pi square over gme times r cube, okay? As you can see, all of this in this bracket are constant. So what we can say is t square is directly proportional to r cube, and this is the third Kepler's law of planetary motion. Okay, so we have derived three things. We have derived the escape velocity equation, we have derived the satellite velocity equation, and the last one we have derived the third Kepler's law, which tells us about the period of a satellite. Okay, so that is the end of this video. Thank you very much, and I'll see you in the next video.